Adam Smith famously proposed that the free market is guided by an invisible hand. To understand the logic behind this theory, we can use a specific mathematical framework to track how individual choices build into a collective outcome. We'll start with 4 individual actors. On the demand side, we have 2 consumers, A and B, each with a demand equation of 30 minus P. On the supply side, we have 2 firms, 1 and 2, each with a supply equation of simply P. To determine how the entire market behaves, we aggregate these individual equations. We do this by adding their quantities horizontally, focusing on Q, not prices. Adding the 2 consumer demands gives us a total market demand of 60 minus 2P, while adding the 2 firms gives us a total market supply of 2P. Market equilibrium occurs at the point where aggregate supply equals aggregate demand. To find it, we set our 2 new market equations equal to each other. By adding 2P to both sides, we get 60 equals 4P, resulting in an equilibrium price of 15. Substituting that 15 back into our supply equation gives us an equilibrium quantity of 30. Our market settles at a specific coordinate, 30, 15. These individual behaviors have condensed into a single market reality, where every trade is dictated by that one equilibrium price. Converting this data into a graph allows us to measure the specific economic benefits of these trades. By setting quantity to 0, we find the y-intercepts, a price of 30 for the demand curve and 0 for the supply curve, with both lines meeting at our equilibrium point. The blue area represents consumer surplus. This is the value gained by consumers who were willing to pay more than the market price of 15. We calculate this area by taking 1/2 the base of 30 times the height of 15, yielding a surplus of 225. Now, try calculating the producer surplus, the area above the supply curve and below the price. With a base of 30 and a height of 15, the calculation is identical. 1/2 times 30 times 15 equals 225. Summing these values gives us a total surplus of 450, representing the combined benefit that buyers and sellers received from participating in this market. We know that 30 total units moved through the market, but we can also determine exactly how those units were distributed among the 4 original actors. The equilibrium price serves as a coordinate that tells every participant how to act. If we substitute the price of 15 back into the individual demand equations, we find that consumer A and consumer B each receive 15 units. On the supply side, plugging 15 into the firm equations shows that firm 1 and firm 2 each produce 15 units. This micro-allocation of 15 units for each participant sums to our macro market quantity of 30. Without central planning, the market price has coordinated these individual actions into a stable distribution. With a total surplus of 450, we can now test if this outcome is the most efficient state possible. Consider what happens if we stop production early at a quantity of 20. This leaves a gap of unshaded space on our graph, potential trades that never happened. This gap is deadweight loss, meaning the total value to society has decreased. If we push production to a quantity of 40, we run into the opposite problem. Past the equilibrium point, the cost of production exceeds the value to the consumer. This red area represents negative value that subtracts from our total surplus. The equilibrium point is the only mathematical position where the area of surplus is maximized without incurring these losses. This result is the core of the first fundamental theorem of welfare economics. It proves that under perfect competition, the market naturally reaches a Pareto Optimal state, a situation where it is impossible to make one person better off without making someone else worse off. To solve, follow this sequence. Aggregate individual equations horizontally, find the equilibrium, calculate the total surplus, and then plug the price back in to find individual allocations. You've just built a mathematical proof of the invisible hand using the first fundamental theorem.